This is a video for the third time on weak acids and ionization constants. We saw in previous videos that when we wanted to find the concentrations of the species that are produced when an acid dissolves in water, or if we wanted to find the pH.
And Jacob Tarnowski, please come to the counseling office.
I hope you guys got that. If you are either one of those people, please report to the guidance counseling office. Anyway, in previous slides or in previous videos, we saw that if we wanted to find the concentration of the hydrogen ion or the anion associated with the acid or the pH, that we could do this easily because we know that strong acids ionize completely. So if we're talking about a strong acid, finding the concentration of H plus and the concentration of the A minus, since strong acids dissociate completely, we could just use stoichiometry to try to figure out what the concentration of each of those species was, and then just use minus the log of the H plus concentration to find the pH. Well, it's not quite as easy for weak acids because remember, weak acids do not completely dissociate. And so we have to do something a little bit different in order to find the concentration of H plus, A minus, and also the pH of the particular solution. So here is an example of a generic acid, HA, reacting with H2O to form H3O plus and A minus. And of course the H is being donated, the proton is being donated, the H plus ion being donated to the water molecule to form H3O plus, and what's left over is the conjugate base of the HA, which is the A minus. And of course we see that it's in equilibrium, so it's telling us that the reaction is reversible. It's not going to completion, not 100% dissociation. And of course we can rewrite the equation this way, taking the water out of it and simplifying it so we can just see what's going on with the proton, as we discussed previously. Of course, since this is an equilibrium equation, written as an equilibrium, we can write an equilibrium expression for it. And the K sub C, in this case, is equal to the H plus concentration in equilibrium times the A minus concentration in equilibrium divided by the HA concentration, also at equilibrium. Because this is a special K, get it, special K, because it is a specialized K that is specific for acids, we call it the Ka, which is known as the acid ionization constant, K sub A. The greater the Ka, the stronger the acid's going to be, which seems to make sense, because the greater the Ka, that means the more that this dissociates. The more of these two species we're going to have in solution, the less we're going to have of this one. The greater the Ka, and therefore, since we're going to have more H plus in solution, which is actually H3O plus, the stronger the concentration of this will be, or the higher the concentration of this will be, and the stronger the acid is. Here is a list of some different weak acids, and shows their structures, and it shows their Kas. There they are. The strongest one being here the formic acid with a 1.7 times 10 to the negative fourth Ka, and looks like the weakest one is probably going to be our hydrocyanic acid with 4.9 times 10 to the negative 10th, because remember, the larger the Ka, the stronger the acid's going to be. Here is a list of their conjugate bases, and here's something known as Kb, because obviously, my friends, and we're going to talk more about this later, but obviously we can see that if we've got an acid, and since we've talked about this before, or maybe we haven't, maybe we're going to talk about it in the future. Anyway, you've got a weak acid, and remember we said that its conjugate base has, it's not a strong base, but it has significant base characteristics. And so the weaker this acid is, the stronger this base is going to be. And so these are some of the stronger acids, and we've got weaker bases, and these are some of the weaker acids. And these end up with stronger bases, and this is what's called the K sub B, which we're going to talk about more in the future. So let's do a problem. It says, what is the pH of a 0.5 molar HF solution at 25 degrees Celsius? Well, there's the equation that represents the process. And we know that the Ka for this equation in equilibrium is H plus concentration times the F minus concentration divided by the HF concentration. And then that's equal to 7.1 times 10 to the negative fourth, which we can find from the chart in the previous slide. So let's rewrite the equation, And the way we're going to solve this is through an ice equation, or an ice setup, an ice formula, an ice chart. So we're going to do the initial concentration, change in the concentration, and the equilibrium concentration. You see, this is an equilibrium, and we're looking to find the H plus here in order to find the pH, because you know from the previous video that pH is equal to minus the log of the H plus concentration. So we need to get the H plus concentration, which means we need to find the concentration of the H plus in there, and the other species too, so that we can figure out the pH. And so since we are working with a weak acid and we're trying to find the concentration of species at equilibrium, we have to do the ice chart just like we did in the last chapter. So the initial concentration of the HF is 0.50. And of course the other two are just 0, because remember, this is the initial concentration of HF. It's the concentration of HF as you just put it in the water before anything happens. Now, we're going to assume that the HF is going to decrease in concentration, and we're going to choose the variable x. So we're going to say it's decreasing by x. And of course, since this is a one-to-one relationship between the H plus and the HF, the H plus has to be increasing by x, and since this is a one-to-one relationship between the HF and the F minus, that has to also be increasing by x. So at equilibrium, the HF concentration is 0.50 minus x, the H plus concentration is x, and the F minus concentration is also x. So we take the Ka equation, because really this is the only way we're going to find these species concentrations at equilibrium.
Jacob Tarnowski and Fatty Del Greco, please come to the counseling office.
If they wanted to, they would. Or if they were here, they would. Anyway, so the concentration of H plus is x, and the concentration of F minus is x, so that becomes x squared. And the concentration of HF at equilibrium is 0.50 minus x. So the way it looks right now, we'd have to cross multiply here, come up with a quadratic equation, and then use the quadratic formula to solve it. But we're going to make an assumption. Ka is much, much, much less than 1. We're going to say that Ka is a lot less than 1. It's a small number. So we're going to say that since Ka is such a small number, in reality the value of x is really, really small compared to 0.5. Not that 0.50 is a huge concentration, it's pretty dilute, but we're going to assume that x is really, really small compared to 0.50. And therefore, 0.50 minus x is approximately equal to 0.50. So when we make that approximation, we can actually remove the x from the bottom of the equation, which makes this much, much easier to solve. And so x squared is 3.55 times 10 to the negative fourth, which we got from multiplying the 0.5 times the 7.1 through a cross multiplication. Then taking the square root of both sides, we get x is equal to 0.019. Which means that since the H plus concentration, which is equal to the F minus concentration, which are both equal to the quantity x, x is equal to 0.019, therefore they are both equal to 0.019. And of course the HF concentration is 0.50 minus 0.019, which is x, so that comes out to 0.48. Now, we have to make sure that we check this approximation to see that it is okay. We just can't assume that this is a great approximation to do. And so, oops, sorry about that. I forgot to tell you that we're going to find the pH, because that was the reason that we did the problem. And so we plug in the H plus concentration, which is 0.019. We take minus the log of that, and we get the pH. All right, let's try again. Here we go. When can we use this approximation? Do we have to check the approximation? Yes, we do. Well, the Ka is much, much less than 1, and so we made this approximation. We have to make sure that when we make this approximation that the value of x is less than 5% of the value from which we subtracted from. So we take the 0.019 and we divide it by the 0.50, multiply it times 100, comes out to 3.8%. So hey, it's less than 5%. If it's less than 5%, this approximation is good, and we can keep the numbers, and that's how we solve the problem, based upon that approximation. Let's take a look at a similar problem, only instead of using 0.50 molar HF, we're going to use 0.05 molar HF. So again, we do an ice problem, and the concentrations of the H plus and the concentrations of the F minus would come out to be X each at equilibrium, so that's X squared, and the concentration of the HF is 0.05, and that would be minus X, but again, we're making that approximation and assuming that X is really, really small, and when we do that, the X on the bottom goes away like we did in the previous problem, and so we solve for X, and X comes out to be 0.006, which now we're going to check because remember, this concentration of HF, now the concentration of HF at equilibrium would be 0.05 minus this value of X. And so we'll check to see if X is actually less than 5%. And as you can see, it's not. It's not less than 5%. And therefore, we can't use that approximation. So it's not good. Not a good approximation. So we must solve for X exactly using the quadratic equation, or what's known as the method of successive approximations. Ask me about the method of successive approximations tomorrow. So, this is a list of how to solve KA problems. Whoops, sorry, let's go back for a second. And you can stop and you can write this down if you would like. If you don't want to, you don't have to, but you can write all these things down, take a good look at it. I'm not going to read them to you because you can read them yourself. And we're going to move on to the next problem. What is the pH of a 0.122 M monoprotic acid whose Ka is 5.7 times 10 to the negative 4? So we're going to write the general equation for this acid, and we're going to do the ice chart because remember we want to find the pH, which means we need the H plus concentration in order to find the pH, and since this is a weak acid we'll have to do it using the ice chart. Initial concentrations of each, assuming that the HA is the one that's decreasing and it's going to decrease by the amount of X. Since the relationship between HA and H plus is 1 to 1, H plus is going to increase by X. Since the relationship between HA and A minus is also 1 to 1, A minus is going to increase by X. Here are our equilibrium concentrations. And of course, we're going to plug those values into our Ka equation. Remember, it's the H plus concentration on top times the A minus concentration, so that's X times X, which is X squared, divided by the HA concentration. So it's the H plus times the A minus concentration, X times X, X squared, divided by the HA concentration on the bottom. Assuming that our Ka is really, really small, and that X, for all intents and purposes, compared to 0.122 is really not going to make a difference. So when we subtract the two, we're going to get approximately 0.122 anyway. And so we get rid of the X, and then therefore the Ka is approximately equal to X squared over 0.122. Solving for X squared, and then for X we get 0.0083.
Maddie Del Greco and Jacob Tarnowski, please come to the counseling office.
So we get 0.0083. Apparently those people don't want to go. Which we can see is greater than 5% of the 0.122. So that means we cannot solve it using this approximation. We will have to use the quadratic equation, or the method of successive approximations, which you should ask me about. So when we use the quadratic equation, or the quadratic formula, we come up with two values of X. Now obviously the value on the X, a value of X on the left is the correct one, the value of X on the right is not the correct one, because it's negative, and if we actually subtracted the negative 0.0081 from the 0.122, it would actually get larger, and that would tell us that the HA concentration actually gets larger, which doesn't make any sense. So it can't be that one, it's got to be this one. So remember, in the ice equation, equilibrium concentration of this is 0.122 minus X, the concentration of this is X, and the concentration of this is X also. So that means the H plus concentration is X, and of course the A minus concentration is also X, and they're both 0.081, and the pH would be minus the log of the 0.0081, which is 2.09. And of course, remember to find the HA concentration, that's 0.122 minus the 0.0081. Okay, let's hope this sticks. All right, I'll see you tomorrow. Hopefully you've got questions. If not, fantastic.